Hi everyone, my name is Zaineb Bani-Yassin. Today I'm going to be presenting my Milestone 5 project on topical medication absorption using differential equations. And this is a real scenario that physician assistants face every single day in their practice. So the question I'm answering today is when a PA applies antibiotic cream to a patient's skin infection with continuous reapplication, how does the medication concentration build up over time? And when does it reach a stable therapeutic level? So let me walk you through how I solve this problem using math approximation methods and real-world application. So let's see the scenario first. Imagine a physician assistant is treating a patient with a skin infection using a topical antibiotic cream. The PA continuously reapplies the medication at a rate of 75 milligrams per square centimeter per hour. At the same time, the patient's body is absorbing that medication into deeper skin layers. The absorption rate is proportional to how much medication is currently present, specifically 30% concentration is absorbed each hour. So these are the variables of the equation. X represents the time in hour starting at 0. Y represents medication concentration in milligrams per square centimeter, also starting at 0. So the rate-in is 75 milligrams per centimeter per hour, and that's the continuous application. The rate-out is 0.3 Y, and that's the absorption. This depends on how much is there I'm monitoring for 20 hours and see the concentration changing. So why does that matter exactly? Understanding this helps PAs design better treatment protocols, predict when the medication becomes effective, and explain to patients why consistent application is important. Okay. So now getting into the math, the scenario is described by differential equation, and the differential equation is dy over dx equals 75 minus 0.3y. So breaking down what that means is dy over dx is the rate change of the medication concentration over time. The 75 represents the medication being continuously applied. That's our rate in. And the minus 0.3y represents medication being absorbed, and that's our rate out. And then when you add them together, you get the rate of change. So to solve this differential equation, I use separation of variables. I separated the equation so that all the y terms are on one side and then all the x terms are on the other. Then I integrated both sides after applying my initial condition that at time 0, there's 0 medication, and then I get the exact solution, which is y equals 250 between parentheses 1 minus e to the power negative 0.3x. Okay. And then, so now we're doing the Euler's method. The Euler's method is a numerical technique that approximates the solution by taking small steps forward in time, calculating the concentration at each step. So first I did the H equals 1, and then the H equals 2. So with the step size of H equals 2, I calculate the medication concentration every 2 hours instead of continuously. And here's what I found. So these are the hours I use, and then this was the medical concentration. So yes. And then looking at the graph, notice that the red dots start at the origin, and then they follow the general shape of the blue line. The dots are fairly close to the line, which shows a pretty good approximation. The medication concentration increases rapidly at first, then the curve flattens out as it approaches equilibrium around 250. Yeah, right here. 250 milligrams per centimeter square. And then by 16 to 20 hours, the concentration has reached its maximum. So then I did with the 4. So, like I said, I did the h equals 1, and because it's a smaller number, it has more approximation than h equals 2. So now looking at what h equals 4 is, now we're trying the much larger size. That means we only calculate every 4 hours instead of every 2 hours. So this is what I got, and then now if we look at the graph, what do we notice that's different? Now we only have 6 red dots in total at 0, 4, 12, 16, and 20 hours. The red dots are noticeably further from the blue line. There are huge gaps between the calculations where the approximation completely misses what's happening. So the fewer calculations means there's less data, the less data means there's bigger gaps between the points, and the bigger gaps mean the approximation can miss important details about how the medication concentration changes. So the h equals 4 approximation is clearly less accurate than h equals 2. Okay, and like I said, they use, in real medical software, computers use even smaller sizes, like h equals 0.1 or h equals 0.01 to be as accurate as possible. So when I put in the actual values, the difference is clear. At 10 hours, h equals 2 gives us 1.59 milligrams per centimeter square compared to the exact answer of 159.3. That's basically perfect. But h equals 4 gives us 1.47.8 milligrams per centimeter square, which is way off. And then at 20 hours, h equals 2 is at 245.8 versus the exact 246.9. But the h equals 4 is at 226.5, and that's a 20 milligram per centimeter squared difference. So the answer to which step size is better is clearly h equals 2. And in real medical software, like I said, programmers use even small step sizes to be even more accurate. So let me talk about the equilibrium, the steady state where the medication concentration stops and the changing levels are off. To find the equilibrium mathematically, I set dy over dx equal to 0 because at the equilibrium, there is no more change. So 75 minus 0.3y equals 0. So we're solving for y 0.3y equals 75, and then the y will equal 250 milligrams per centimeter square. So what does that mean? After about 15 to 20 hours of continuous application, the medication concentration stabilizes at 250 milligrams per centimeter square. At this point, the amount being applied, 75 milligrams per centimeter square per hour, exactly equals the amount being absorbed. And the system is a perfect balance. So what does the equilibrium tell the PA exactly? So the medication will never exceed 250 milligram per centimeter square with continuous application. If that concentration causes irritation, reduce the application size, and if that concentration isn't therapeutic enough, increase the application rate. The treatment is stable and predictable after about 15 to 20 hours. So to summarize what we learned, first we started with the real clinical problem, a PA treating a skin infection with continuous topical medication, and then I created a differential equation to the model situation, which was dy over dx equals 75 minus 0.3y. The equation captures the balance between the medication being applied and the medication being absorbed. And then we solved analytically and we got the exact solution, which was y equals 250 between parentheses 1 minus e to the power of negative 0.3x. And this tells us exactly what the concentration we will be at any time. Then we use the Euler's method to approximate the solution, comparing step sizes h equals 2 and h equals 4. I learned that the smaller sizes give us better approximations because they capture more detail. I found the the equilibrium at y equals 250 milligram per centimeter square and explain what that means in a PA practice. So what we learned, the bigger picture was mathematics isn't abstract, it's a tool for solving real problems. And as I prepare for a career in physician assisting, I realized that thinking this way breaks down complex clinical situations into mathematical problems, solving them and interpreting results. This is exactly what I'll do every single day, so thank you for reviewing my project. I'm excited about bringing this analytical thinking to my future role in healthcare. Thank you.